Hello, everyone. Sort of happy Friday, and this was something getting on, but proving again that Chrome works and other browsers don't. All right, so again, happy Friday, and finally, welcome to my talk. So today I'll focus on sort of data handling for building predictive models using machine learning. Right. So more specifically, what I'm going to talk about is a particular data property that significantly impacts the resiliency characteristics of models that are powered by that data. So first, a little context. So my name is Anindya Datta, and I work for a consumer intelligence company called Mobilewalla. So where we sell data and feature artifacts, that improve the predictivity of predictive models. Right? So these artifacts themselves, in most cases, are the output of machine learning models that we build and maintain in-house. So currently, we operate about 30 models in production and continue to deploy 1 to 3 additional models per quarter. So these models, as you can imagine, are mission critical for us as their output turns into our market offerings. So the work that I report in this talk was motivated by the problems we faced in building and running these models. Right? So most of our models are powered by large amounts of data. Each day we ingest about 25 terabytes of new data into our internal repositories. And our models typically run periodically, say once a week or once a month. So this means that for a given run, the amount of data that gets pipelined in for treatment is typically in the low hundreds of terabytes or sort of near petabyte ranges. While this may sound like a lot, from frequent interactions with our users, who are typically sort of members of data science teams from large companies, telecom, retail, finance. So we know that machine learning data pipelines at their companies routinely handle as much or even more data. Right? So the biggest problem our data science team and many of our users face is model resiliency. Right? So while models work super well in testing, their performance in production is often asymmetric. Right? So for us, this is a big problem. So when we started out about 4 years ago, so we were hyper-focused on building models with high predictivity, sort of squeezing every iota of Guinea lift before deployment. So over time, our views have changed a lot, right? So at this time, we would rather have resilient models that provide sort of sustained performance with acceptable sort of accuracy than ones that hit it out of the park at testing but misbehave in production. This is a problem we all know. So to address this mission critical issue, our data science team has, over the past few years, devised a number of in-house innovations. This talk is about one of them, right? So let me end this introduction with a quick background of myself. Prior to founding and running Mobilewalla and a couple of other ventures, I used to be a faculty member at Georgia Tech, where my area was data and AI. In particular, I was sort of deeply involved in both the undergraduate and graduate AI classes. And most of my grad students at that time were doing research in AI. So that's the context, and because I'll focus sort of on the data pipeline part of the machine learning workflow, I thought it would be useful to quickly get us on the same page on what that workflow is, right? So in this slide, I depict the canonical version of this. I mean, you all know this. So enterprise data systems sort of content-based data, which is run through a process of transformation to produce features. This process, one of the most impactful steps in machine learning is known as feature engineering. The engineered features are then combined with learning algorithms in the model engineering phase to produce models which are trained and tested. Finally, when acceptable performance is reached, models are deployed and powered by features that come from operational data sources. So this is nothing new. And my assumption is that every member of the audience is sort of well aware of this workflow. So now I come to the core driver of this work, the quest for model resiliency, right? So what is resiliency? Well, resiliency is a property that dictates sort of how likely a model is to conform to its performance profile at testing. Right? Put another way, when you deploy a model because it performed a specific way at testing, resiliency kind of dictates how well the performance of the deployed model will mirror the performance of the same model at testing. Right? So as is well known, the lack of resiliency is one of the biggest problems that modelers and machine learning sort of MLOps professionals face. Models misbehave in production all the time. Right? This not only makes the life of machine learning practitioners difficult, it also greatly impacts the trust that ops leaders, like the operational leaders that owns the business processes, have in the use of models to run those processes. Right? It is generally agreed that building resilient models is fundamentally important to the widespread adoption of machine learning in organizations. Right? So here is a quote for somebody who's super well known in the machine learning. I think we can all agree that building resilient models is one of the most important problems at this time. So talking about the lack of resiliency, so let's consider why models break. Right? So while there are many reasons for this, one of the most common is the change in the properties of the data that power the model. Right? This is known as data drift. So the model performance expectations are set at training and testing times. But when deployed, if the distribution of the data items change, the model performs unexpectedly. And as every machine learning practitioner knows, the distributions of ingested data is almost never static, particularly for certain attributes, making model resiliency a core problem. Also, in many organizations, models are trained and tested either on synthetic data or kind of insights data, where models are powered by operational data. So that's another reason for sort of lack of data drift as well. Right? So because data drift is such a well-known issue, almost every ML tool provides ways to measure it, right? So I'm sure the audience of this talk are aware of the diff utilities offered widely. But all of them, effectively have the same canonical form, right? Which I show in the screen on this slide. So you put two distributions into this utility, into the drift package. Usually the distribution used at training, which set expectations of performance, and the distribution input into the deployed instance, which has misbehaved, right? So the source and the target. And the utility provides you a measure of distance between those two distributions, which is basically a measure of drift. If this exceeds preset thresholds, this triggers, this attribute is regarded to have drifted, and kind of remedial procedures are initiated, right? Often this involves retraining the model. So it is, of course, obvious that models are not anchored on one data or one feature. There are a whole number of data inputs into a model. So when something breaks, going through this process, which is almost always done, is a very costly and time-consuming procedure. It's an exhaustive forensic exercise, right? And I'd like to reiterate that drift identification, as it occurs currently, is a very much a reactive forensic exercise, right? A model misbehaves, drift identification occurs, and the model is fixed. In other words, while drift utilities are valuable in helping identify and fix root causes, they're not directly helpful in building models that are resilient by design. Of course, we know we have machine learning ML engineer friends who try to circumvent this by building a priori kind of measurement tools, but those are kludgy systems that are built by hand in-house. The point I'm making is that existing tooling really is forensic. Right? So tired of building models that seemed awesome at testing but broken deployment, we started to think about how to build resilient models from scratch. Right? So let me take you through our thinking. It went like this, right? So we know that perhaps the primary cause of performance asymmetry of models is the drift of data. And we also know that different data items drift differently. So an intuitively obvious way to improve model resiliency is to preferentially use to build models data that drifts less, right? So if you use data that drifts less, you should produce models that perform, misbehave less. I mean, that's the intuition. But to pull this off, though, we would need to know the drift properties of data items prior to their being actually used, right? So effectively, we need a priori knowledge of how likely each attribute is likely to drift over time. Right? So for the past 3 years, we have been trying a variety of ways to measure the likelihood of data drift. And we believe that we have finally devised a metric that appears to work really well. So we call this metric data stability. And let me give you some details on that, right? So as I just described, so stability captures the driftiness of data, right? So if attributes A drifts less over time than attribute B, so A is more stable than B. That's the idea. And for the mathematically inclined among you, if you go back to your high school calculus, I mean, think of stability as the first derivative of drift, like d drift dt. So in our implementation of stability, so we represent stability as a continuous variable ranging from 0 through 4, where 0 indicates something that is very unstable, low stability, and 4 is high stability. Right? And we compute stability by observing a distribution over time and recording how it changes over time, right? And in order to record that, we consider 4 sort of fundamental characteristics of a distribution. Central tendency, dispersion, skewness, and shape, right? So there is a lot of evidence in mathematical statistics, but these, if you define these, you sort of know the distribution. So the intuition is quite obvious above, I think. So there were sort of 2 challenges that we have had to overcome to actually manifest the stability metric, right? So one is, it's easy to say that, hey, it's sort of central tendency, dispersion, skewness, and shape are the core sort of parameters of a distribution, so we'll see how much they shift. But it's yet completely another thing to build a closed form formulation of the stability metric. Right? So one mathematical expression, if you will, that nicely captures stability. So that was sort of one thing that we worked a lot on. And then eventually once we eventually arrived at something that appears to work well across a wide range of sort of applications. And then the second challenge was computing this at scale, right? I mean, these are very computationally complex sort of things, and sort of and doing this again and again is very is complex. So what I'm telling you is that we finally seem to have sort of addressed these 2 problems nicely, and so we have finally operationalized stability computation throughout our modeling pipeline, right? And the results, sort of, I'm happy to say, have been like really good, right? So I can spend another 30 minutes just talking about the impact that stability has on the models we create, but we don't have the time. But feel free to get in touch with us after this talk or later, and our data science team would love to catch you up on the results that we are seeing using stability, right? So finally, let me say a few words about how factor in stability in our machine learning pipelines, right? So as a matter of routine, we assess the stability of all relevant data items. So these are data items that have proven to impact features and models. And this assessment is available continuously to all our modelers and MLOps folks, right? The most important impact of data stability is on our feature engineering sort of process, right? I mean, to put it simply, we prioritize stable data to construct features, right? To add more color, so when creating features through data transformations, the modeler is provided access to the stability properties of all the base data items sort of at her disposal. And this allows her to create sort of stable features, right? Features. And by the way, so I'm using this notion of feature stability. So this is something also that we have defined, which I don't quite cover in this talk, but feature stability is a function of the stability of its constituent data items, right? And that's a topic for another day. But the bottom line, in the model engineering process, we try to build models powered by stable features. And stable features are, of course, features built through stable data items. such that the resulting models have predictable performance. So I should add that there are times when data with modest, or does this mean that, hey, data items that are not very stable never get used? No. I mean, there are lots of data items that are not stable. And there are times when data with modest stability does get used in creating features. Typically when the predictivity of that feature is so high that it warrants accepting, it warrants sort of being a low stability feature. But even in this case, the stability properties are known in advance, right? Unlike finding sort of when a model is deployed. These are known in advance. And that allows our ops teams to prioritize monitoring those models, right? So given that model monitoring at scale is super costly, stability computation allows resources to be preferentially dedicated towards models that have weaker expected resilience, right? So far, I've been sort of hand waving about stability and its uses in feature engineering, giving you sort of vague ideas. Let me fix that now, right? So we are launching an open source project called Anovos, where we are making available the entire feature engineering automation workflow that we have built in-house, right? So this is sort of driving significant results, not just for us, but also at some of our large clients. So Anovos, as I discussed briefly in this talk, in Anovos we are introducing sort of a different way to perform feature engineering that helps build resilient models. Unlike existing approaches that address model breakage through reactive and forensic means, Anovos encapsulates a data pipelining process that allows building resilient models from the ground up, right? So internally, Anovos incorporates two broad modules, right? Data ingestion, preparation, analysis, that's one module, and data transformation, creating features through transformation, in which cleaned and prepped data sort of is transformed into features. So we are about to launch part one of Anovos, that is the ingestion, analysis, and preparation part, with the transformation model soon to follow. And of course, in the ingestion, analysis, and preparation part, we are opening up sort of drift and stability computation that we just talked about, and many other things. So the best thing about Anovos, at least for us, is that it's produced by an experienced data science team to sort of address everyday problems that data scientists face, right? And it has proven out not just well for us, but now a number of sort of very smart data science teams across the world. So, and it gives me great pleasure to invite you to join the Anovos family and both use and contribute to the project. Right? We have addressed some of the hard problems, but many, many more remain. My hope is that together we can create a truly transformative platform, free for all to use and enhance, that fundamentally improves our ability to build models that don't break. So thank you, and hopefully, I was able to do this kind of quickly. Are we still live? So I'm done with the talk, guys. Okay, I see. Any questions? Anything? Well, if there are no questions, then Brian asks, who is Anovos' main competitor? I mean, Anovos is of course a open source tool where the idea is to have this open. Um, on the feature engineering side, probably, if you think of Anovos as having two sort of significant components, one is sort of the data ingestion, analysis, prepping, cleaning part, and the other is the transformation. Effectively, how do you create features, solving the cold start problem, selecting your features based on impact, and stability. On the analysis side, there are definitely tons and tons of sort of options, right? I mean, every every software tool, right? Whether the native ML pipelines that cloud providers offer, like SageMaker on Amazon, or ML Studio on Azure, or any of the other, like Data Robot. Everybody has a data analysis tool. On the open source, if the Pandas framework definitely allows for analysis. So in that case, you can think of those as sort of Anovos' competitors from a data analysis perspective. But where I think we are trying to advance the state of the art, and as an open source tool, and this is not sort of our core business, so we are not really thinking of who our competitor is, but but we think sort of we are advancing the state of the art sort of on the ingestion side in three ways, right? So one is, all these tools have a whole bunch of kind of analytics which are repurposed from sort of data engineering kind of user base, right? So we like to think that we have the set of analytics that data scientists need, which is slightly different than what data engineering does. I mean, you got to play around with the package to really find out. Scale. If you think of, let's say, Pandas, I'm sure there are many Pandas users there. Typically, you download Pandas on your laptop, and you can use it on 2, 3, 4 gigs of data. Anovos is created for you to input literally. There is really no limit, right? I mean, a laptop these days can hold 100 gigs of data. We have our folks and other folks that are working 50, 60, 70 gigs of data running through Anovos and getting scalable performance. But probably the most important component of Anovos that is different is the stability and drift analysis, right? So that is really where I think we end up revealing metrics, end up revealing data properties that are fundamental to creating sort of good models going forward. So that's sort of on the analysis side. And on the transformation side, guys, I at least and again, our data science team will be able to, I'm sort of, I hang out with those guys. From at least from me, all packages provide you a transformation environment. Right? You'll have a notebook, you'll have a set of prepackaged transformations. But we are really trying to, but what we have, and we use this in-house, and we'll make it available soon, is we have a very, so we have a feature recommender, right? I mean, you should be able to come in and say that, hey, I'm trying to create a model for predicting, affinity for travel insurance. I'm a travel insurance, company like MetLife or something, right? I mean, the travel insurance guys come to the data science team and say, hey, we want to target offers. Tell us what makes a person, So the idea is, so what we have built is sort of a feature recommender, right? You should come in and say that I'm trying to build models of type X. This is sort of the environment I'm working in, and the system should be able to tell you that, okay, here are 15, 20, 30 features that you might find useful, right? So there are, on the transformation side, we believe that there are some fairly unique things. But on the analysis side, definitely, almost every tool, there's a ton of tooling for data ingestion analysis. We believe that what I presented is sort of very interesting and hard and kind of unique. But definitely there are other people that are doing sort of analysis. I hope that gives you a reasonable answer. But again, the point here is not really compete. The point is to, so we are opening up things that have proven good for us that we couldn't find outside. Yeah. So, so we're not really thinking so we are opening up what has proven useful to us, and we believe, and which we couldn't get outside, and there are a ton of things that we don't address yet, right? So I'm hoping that there can be a groundswell of sort of activity around ANOVOS, which can really create something that is truly disruptive. All right. If there are no further questions, we can, I'll ask the administrator should we end the session?